Hey, my name is James DeBiser. I am from the Stratospheric Observatory for Infrared Astronomy, and I'm here to talk about the largest and brightest massive star-forming regions in our Milky Way. And what I'm really talking about are giant H2 regions, and these by definition are regions that have Lyman continuum photon rates of 10 to the 50 photons per second or greater. Now, this is much larger than any single O star can produce, and so we're really talking about regions that are being ionized by clusters of OB stars, very massive clusters of OB stars. There are about 50 bona fide IR bright GH2 regions in the Milky Way. There's a survey by Conti and Crowther 2004, where they give this list that we use as our source list. And that's about a typical number for a spiral galaxy. If you look at an external spiral galaxy like M51 here in the background, you'll see all the little red splotches. Those are giant H2 regions. These are the areas where the most brightest star formation, the most massive star formation is occurring. And so we can learn a lot about external galaxies from studying giant H2 regions because these regions actually dominate the total bolometric luminosity for most galaxies. So our motivation is to learn about the physical properties of giant H2 regions, both individually and as a population, to see what we can learn from them and see if we can use it as a template for what we can't resolve in external galaxies. And we're going to use SOFIA and Forecast for this. Forecast is a mid-infrared instrument on SOFIA that works from 5 to 40 microns. Our goal is to observe as many of the giant H2 regions in the Milky Way as possible, completely covering their mid-IR emitting regions, and to do that at a wavelength that has not been achieved at wavelengths beyond 20 microns. And we're also going to try to quantify the massive young stellar object population because that's something that in many cases can only be traced in the infrared. What do I mean by that? So here's W3. W3 is a massive star forming region. It's not a giant H2 region. The most massive luminous source in here is this 500,000 solar luminosity IRS5. It's very, very bright and apparent in the mid-infrared, as you see here on the left. But there's no radio emission coming from it at 2 centimeters, as you can see on the right. And this is a part of the evolution of a massive star that's prior to the onset of a ionized region around it. So if we really want to find all the massive young stellar objects in a region, we need to look at the radio and the infrared to look for these most embedded sources as well as the ionizing sources. Now, why didn't we just use Spitzer? Well, Spitzer, this is M17. M17 is one of our giant H2 regions, and this is a Spitzer image of it. And you can see, even though Spitzer has a very good resolution of 6 arc seconds at 24 microns, all the black in the center of this image is saturation. We have no information about the brightest and most interesting parts of M17 here. There's MSX. MXX doesn't saturate, and so we have this nice image of M17, but it has 18 arc second resolution. So there's a lot of detail being missed here. And now we can show you the image of what we see at SOFIA at 20 microns at 2.5 arc second resolution. So you see as we go back and forth between the MSX image and the SOFIA image, what an order of magnitude, almost an order of magnitude increase in spatial resolution gives you. You can see a lot more detail of the individual sources and environments inside a giant H2 region. Now, Forecast can take 2 wavelengths of data at the same time. We did 20 microns and we did 37 microns. And 37 microns allows us to probe even more embedded sources and see things that might not be seen even at 20 microns. Now, you might say, well, surely ground-based observatories have looked at M17. And yes, a lot of these giant H2 regions have been looked at with ground-based observatories, but usually they concentrate on the brightest sources like this one here in the center. And this field of view here that I'm showing here in purple is the field of view of Gemini. It was 30 arc seconds by about 20 arc seconds. And that's about all you can get in one shot with Gemini. And you also had a chop. And so your reference beam was usually contaminated with nearby emission. So you weren't getting very accurate images because you were being contaminated in your reference beam. Now, SOFIA is a lot like a ground-based observatory. We still do have to chop and nod. But the Forecast field of view is 3 arc minutes across. So we're covering a much larger area at a time. And also SOFIA can chop up to 8 arc minutes, which means we can completely chop off the emitting region of a giant H2 region and get very good background subtraction. And for a source like M17, we can map its entire infrared emitting region in this case, 15 pointings, where you'd need an order of magnitude more if you try to do it in a ground-based observatory. And we could take the data that we take from SOFIA at 20 microns and color code it blue, 37 microns green, add some Herschel in as red, and put a Spitzer 3-micron star field in as white, and you get these beautiful 3-color false color images of a region like M17. They're quite beautiful. And we did this for all of the sources that we've done so far. What sources have we done so far? Well, our first publication was of W51A in 2019. This actually is the largest mosaic we've ever taken with forecasts. It's 19 pointings to get this huge area. This region is at a distance of 5.4 kiloparsecs. And actually, W51A is 2 giant H2 regions. The brighter region on the left is what most people think of as W51A, but that's G4 9.5. And we have this more modest luminosity giant H2 region, G4 9.4 on the right. Together, they're W51A. M17 is the next publication that we had, and that was in 2020. And this is one of the closest giant H2 regions to us. It's only 2 kiloparsecs away. The most distant one in our list is, well, one of the most distant ones in our list is W49A at 11.1 kiloparsecs. W49A looks a little bit fuzzier, and that's because it's so far away we can't see it with the same sort of detail that we can for the closer images, closer sources. So we said we wanted to do a massive young stellar object population study. So the first thing we did is found all the point source and compact infrared sources within M17 and all of our giant H2 regions. And then we took their photometry at 20 and 37 microns and added the Spitzer IRAC data if it's not saturated at 3, 4, 5, and 8 microns, and added Herschel data in the Paxton spiral wavelengths that's 70 to 500 microns to create SEDs. Now we took the Herschel data as upper limits because the Herschel resolution is quite poor and we're usually getting contamination from nearby sources. And so we use that as upper limits, but we still get pretty good fits. What do we fit? Well, we fit with the massive young stellar object models of Zhang and Tan. And these give us extinction corrected masses and luminosities for all of our sources, and we can determine which ones are lower mass YSOs and which ones are actually real massive YSOs. So here's a table of that information. You can see that the G4 9.5 region of W51A has copious massive young stellar objects, 34. W49A is no slouch either. It's got 22 massive young stellar objects. M17, though, is has a relatively small MYSO population, and this might be telling us that it's at a stage maybe between starbursts. Don't quite know for sure, but it's a very luminous. M17 is one of the top 3 most luminous giant H2 regions, so it's weird that it has a dearth of MYSOs. In terms of the population of these MYSOs that are non-ionizing, we see in the first 3 rows here, about half or more of these MYSOs are only seen in the infrared. They're not being seen in the radio. And so these data are very important for understanding the total MYSO population. The other thing we did is to look at the evolutionary state within the giant H2 regions. And what we did is we took the centimeter radio contours of these regions that sort of show what the molecular clumps, where the molecular clumps are. So this is a larger scale. We were talking about point sources before. Those are the molecular cores. These are very small things. Molecular clumps contain the cores inside them, so molecular clumps are much larger structures. These are thought to create multiple sources or clusters of sources. And so you see here the 20 centimeter VLA contours. The labels are the radial labels of the individual molecular clumps here. And what we wanted to do is take a look at evolutionary indicators towards these clumps to see what's going on. The first thing we did is we derived a virial parameter for each one of these sources, and that came from CO data that we collected on each one of these regions. We measure the width of the CO line emission. That gives us a measurement of the kinetic energy in these systems. And the idea is that as the systems age, more and more kinetic energy will go into the system. The virial parameter will go up. The other evolutionary indicator that we looked at was the L/M ratio. We looked at the mass of the dust. We calculated that from either JCMT data or Herschel data. And then we looked at the bolometric luminosity, and we did that from basically constructing SEDs from IRAC data, SOFIA data, and Herschel data. And this is another indicator where as the L/M ratio goes up, regions thought to get older. And the reason why is because the mass of dust will go down as it gets incorporated into stars. The luminosity will go up as more and more stars get formed. Now, both of these parameters, evolutionary parameters, are kind of trends, right? You can find gross trends, but there could be some susceptibility to error if you try to figure out the relative evolutionary of a single source. That is, of course, unless you look at both of them at the same time. So here we have virial parameter plotted against L/M, and if you get a nice sort of correspondence like you see here to this line, where basically as the virial parameter goes up for these sources, so do their L/M ratio, you can trust these evolutionary parameters fairly well. And so we see here that G49.5 has, at the lower left, one of the most youngest sources in the region, source B, but also has one of the oldest regions, source H. In fact, all these regions up in the upper right, F, G, H, I, J, if we look back at the map, we see that they are all contained here in the upper left of the image. So there's and the youngest source is this source B here, sort of towards the center. So what this is showing is kind of sequential star formation. The upper left is where the older star formation is, but now in the G49.5, it's all happening down here more towards the middle. And so we see sequential star formation happening. Pretty cool. Did the same thing for M17. Now, M17 doesn't have a lot of radio regions. It has this M17 North bar, M17 South radio bar, and this area up here called the triple. And so we've plotted those, but it also has this region in the middle here where an already revealed population of massive O stars has carved out basically what you're seeing here as M17. A lot of the heating that's going on is by these central stars. And so when we put the trend here, now this is again just the trend to the W51A data only. We see the cavity is up here in the upper right. It's one of the oldest ones in both virial parameter and L/N. That makes sense. One of the interesting things, though, is that M17 North and M17 South lie off this relation. And this has to do, we think, with the fact, again, that there's this older region of very massive O and B stars that are heating up externally, both M17 North and M17 South, and that is creating an artificially larger luminosity. This luminosity is not intrinsic to these sources, and the L/M ratio assumes that the luminosity is intrinsic to the source. So that's skewing these sources off the trend in L/M. We still do think that M17 is the youngest region, not only because of its virial parameter is so low, but because a lot of the massive young stellar objects in this region are actually found in and around M17 South only. W49A is actually quite interesting. The SOFIA data here on the right, shown in gray, has been overlaid with the centimeter radio continuum contours, and all the labels that you see here are for these radio clumps. On the left, in green, are the virial parameter and L/M ratio for these clumps, and we see that they're all concentrated in the center of the diagram. W49A doesn't have any very, very young sources, and it doesn't have any very, very old sources. And so what we're seeing in W49A is perhaps that all the star formation in this region has happened sort of coevally. Maybe it was all triggered at the same time, or maybe not, but it was all done relatively at the same time. It's all pretty coeval. So I'm going to leave my conclusions up because I'm out of time for you to read. But I do want to say that these first three papers covered 4 sources. We have 4 more additional sources coming out in papers this year. One's in the refereeing process, one's about to be submitted, and we hope to make our way through all of the giant H2 regions in our galaxy, or as many as we can, in this survey. Thank you for your time, and thank you for listening.